Our universe holds places that defy every notion of comfort and survival. We are about to journey to 50 of the most extreme environments in the cosmos, from planets with boiling global oceans to stars flung from their galaxies. By the end, you'll possess a new understanding of just how strange and violent reality can become beyond our quiet solar system. We will see worlds where it rains molten iron and explore voids of eternal darkness so vast they should not exist. What single idea about our universe feels the most unbelievable to you? Our journey begins with a world that redefines the very idea of an ocean. Orbiting a dim red dwarf star just 40 light-years away, a planet named Gliese 1214b awaits. This world is a super-Earth, a term that sounds welcoming but is deeply misleading. It is nearly 3 times wider than our own planet and over 6 times more massive. That immense bulk generates a crushing gravity, and it is the key to the planet's true nature. Gliese 1214b is what astronomers call a water world, but forget any image of blue waves under an open sky. Here, the entire surface is a single, endless ocean, yet this is no placid sea. The planet orbits so close to its star that its surface temperature soars to hundreds of degrees. At that heat and under the incredible pressure of its own deep atmosphere and global ocean, water does not behave as a liquid or a gas. It enters a strange fourth state of matter known as a supercritical fluid. Imagine steam and liquid water blended into one chaotic, seething substance. It has the density of a liquid but can flow through solids like a gas. There is no surface to stand on, no shoreline to find. Any probe or ship would sink into a perpetually boiling, murky abyss where the very concept of solid ground is a fantasy. This is not an ocean for life. It is a planetary pressure cooker, a roiling global fluid that shows us how common, gentle water can become an agent of absolute extremity under the right, or rather the wrong cosmic conditions. That endless, boiling ocean is a monument to pressure and heat, but within our own solar system, pressure alone crafts a spectacle of astonishing beauty. Journey to the outer darkness past Jupiter and Saturn, to the ice giants Neptune and Uranus. These are not solid worlds of rock, but swirling spheres of gas and ice with no true surface. Their atmospheres are a deep brew of hydrogen, helium, and a small but crucial amount of methane, which gives them their serene blue hue. Yet descend into their depths and serenity vanishes. Here, pressures build to millions of times what we feel on Earth. At these incredible depths, something magical and violent occurs. The methane molecules, each made of one carbon atom bonded to 4 hydrogen atoms, are literally torn apart. The relentless pressure squeezes the carbon atoms so fiercely they lock into the crystal structure of diamond. Imagine that. Deep inside these distant, frigid worlds, a glittering hail of diamonds is born. These aren't tiny specks either. Scientists believe the diamonds could grow to the size of pebbles or even larger, and then they fall. They rain downward through the dense, slushy layers of the planets, a slow-motion, glittering avalanche drawn toward cores we can scarcely comprehend. This isn't just a poetic idea. In laboratories here on Earth, researchers have used powerful lasers to blast plastic, which contains similar carbon and hydrogen bonds, recreating for a fraction of a second the extreme conditions inside Neptune. And in that instant, they watch tiny diamond fragments form. So while we have never directly seen this storm of gems, the physics tells us it is almost certainly real. A world where the sky, if you could call it that, rains diamonds. It is a reminder that the universe's extremes are not always about destruction. Sometimes they are about unimaginable creation, forging treasures in the dark. Diamonds form under immense pressure, but some celestial bodies experience the opposite force, a violent expulsion so powerful it defies capture. Far from the crushing depths of ice giants in the chaotic hearts of galaxies, a different kind of cosmic engine operates. Here, supermassive black holes hold court, their gravitational influence warping the very fabric of space around them. When a binary star system, two stars orbiting each other, ventures too close to this monstrous gravity well, a celestial slingshot event can occur. The black hole's pull can tear the pair apart, capturing one star into a tight orbit and violently flinging the other away at a staggering velocity. We call these the hypervelocity stars. They are cosmic projectiles ejected from their galactic homes at speeds that can exceed 1 million miles per hour. At that rate, a star is not just moving fast, it is moving faster than the escape velocity of the entire galaxy. It breaks free not from a planet, but from the collective gravitational pull of hundreds of billions of other stars, gas, and dark matter. Imagine a star, a sphere of searing plasma often larger than our own sun, suddenly rocketing into the blackness between galaxies. It becomes a permanent exile, a lonely traveler on a one-way journey into the intergalactic void. It will never again know the crowded stellar neighborhoods of a spiral arm. It will never contribute to the light of a galactic disk. Instead, it sails through an ocean of emptiness so vast that the nearest galaxy might be millions of light years away, a solitary beacon shining where almost nothing else does. These stars are the ultimate runaways cast out by the most powerful forces in the universe, destined to wander the cosmic darkness alone. These stellar exiles sail into a void far more profound than mere empty space. Between the great walls and filaments of the cosmic web lie the true deserts of the universe, regions of staggering nothingness. The grandest of them all is known as the Boötes Void. Discovered in the 1980s, its scale is almost impossible to grasp. This void is a spherical region of space roughly 330 million light-years across. To put that in perspective, if you placed our Milky Way galaxy at its center, the nearest edge of this emptiness would still be over 150 million light-years away in every direction. In a volume of space that enormous, astronomers would expect to find thousands, perhaps even tens of thousands of galaxies. Instead, they have found only about 60. The Boötes Void is not just empty, it is unnervingly, profoundly vacant. It is a hole in the cosmic structure, a bubble in the foam of creation that never filled. For a spaceship lost in its heart, the view would be one of ultimate desolation. You would look out in every direction into a blackness so complete it would feel solid. The pinprick lights of those few, lonely galaxies would be so distant they would offer no comfort, merely emphasizing the impossible gulf between them. There would be no starry backdrop, no faint glow of a neighboring spiral arm, just an eternal, ink-eyed darkness stretching for distances that dwarf human comprehension. This void raises a haunting question: how did a region so vast end up with so little? Its existence challenges our models of how matter clustered after the Big Bang, suggesting that the universe's emptiness can be as extreme and puzzling as its most violent phenomena. Yet within that unimaginable void, a single star would be a monument to isolation. But around a star, matter can gather into forms of shocking violence. Take the planet known as WASP 76b. This is a hot Jupiter, a gas giant like our own, but orbiting so close to its sun that a single year lasts less than 2 Earth days. This proximity creates a gravitational lock, meaning one side of the planet permanently faces its star, and one side is cast into eternal night. The day side is a furnace beyond reason. Temperatures there soar above 4,400 degrees Fahrenheit, hot enough to vaporize iron. On Earth, our water cycle sees liquid water evaporate, form clouds, and fall as rain. On WASP 76b, the same brutal process happens, but with a metal. Powerful, supersonic winds sweep the vaporized iron from the scorching dayside across the terminator, the dividing line between light and dark. As this metallic vapor crosses into the perpetual twilight of the night side, the temperature plummets by over 1,000 degrees. The iron can no longer remain a gas. It condenses, forming droplets in the alien sky, and then it falls. The night side of this distant world experiences a perpetual, glowing drizzle of molten iron. Picture standing on a hypothetical platform there, looking up into a dim, alien sky as droplets of liquid metal, shimmering with their own dull orange heat, streak through the atmosphere. It is a water cycle forged in hell, a testament to how the basic principles of nature can be twisted into breathtaking, terrifying extremes when the thermostat of a world is turned up to stellar levels. Molten iron rain is a spectacle of elemental violence, but some stellar remnants weaponize the very fabric of reality itself. Deep within ancient, glittering swarms of stars known as globular clusters, you can find the densest cosmic graveyards. A place like Turzan 5, a tight knot of stars orbiting our galaxy's core, is a prime example. Within its ancient heart, dozens of stellar corpses called pulsars spin with furious, impossible speed. A pulsar is the collapsed core of a massive star that exploded, a neutron star so dense that a single teaspoon of its material would weigh as much as a mountain. But what makes a pulsar truly extreme is its spin. As it collapses, it rotates faster and faster, just like an ice skater pulling in their arms. Some pulsars complete hundreds of full rotations every single second. With each spin, they beam out focused cones of intense radiation, from radio waves to lethal gamma rays, like a lighthouse of death. If you could stand on a hypothetical planet near one, you would be instantly sterilized by this sweeping interstellar beacon. But in a cluster like Turzan 5, the danger is multiplied. Dozens of these pulsars exist in a space only a few light years across, their intersecting beams creating a chaotic, inescapable web of radiation. The gravitational environment is just as perilous. The combined pull of thousands of ancient stars, mixed with the pinpoint, overwhelming gravity of each neutron star, would warp space-time itself into a chaotic mess. Orbits would be unstable and unpredictable. Any spacecraft venturing into this cosmic boneyard would be torn apart by tides, cooked by radiation, and lost in a gravitational maze from which there is no return. It is not merely a hostile environment, it is a realm where the laws of physics become weapons, enforcing a permanent and absolute quarantine around the dead. While pulsars are cosmic death rays, a more intimate and corrosive hell exists right next door. Venus is often called Earth's twin, a label that could not be more misleading. Beneath its thick, beautiful blanket of clouds lies a world of absolute environmental fury. Those clouds are not made of water vapor. They are a toxic, choking shroud composed almost entirely of sulfuric acid. This is the same highly corrosive substance found in car batteries, but here it forms droplets that fill the entire sky. The atmosphere is so thick that the pressure at the surface is 92 times greater than on Earth, equivalent to being nearly 1 kilometer deep in an ocean. This immense weight crushes and cooks the planet, trapping heat in a runaway greenhouse effect that raises surface temperatures to a constant 860 degrees Fahrenheit, hot enough to melt lead. But the true nightmare exists within the cloud layers themselves. Imagine a probe descending through that sickly yellow haze. It will be pelted by acid rain, but the heat is so intense that the droplets often evaporate before they can even reach the ground, creating a perpetual, corrosive mist. The winds scream at hundreds of miles per hour, whipping the acidic vapors around the entire planet in just 4 Earth days. The few spacecraft that have ventured into this inferno, like the Soviet Venera landers, were engineering marvels of survival. Built like titanium submarines, they were designed to withstand the crushing pressure and searing heat for mere minutes. They transmitted haunting images of a barren, rocky landscape under an orange sky before the environment inevitably won, their electronics frying and their structures dissolving. Venus is not a distant, abstract extreme. It is a vivid, sobering warning of how a world can go terribly wrong, a place where the very air is a corrosive, crushing, and incinerating fluid. Venus shows us a world where chemistry becomes a weapon, but on the frozen frontiers of our solar system, a gentler yet equally astonishing volcanic force is at work. Far from the sun, where temperatures plunge to hundreds of degrees below zero, the moons Enceladus and Europa hide oceans of liquid water beneath their icy crusts. The pressure and heat from their cores, generated by the gravitational tug of their giant parent planets, cannot melt rock. Instead, they power a strange and beautiful phenomenon known as cryovolcanism. Think of it as an ice volcano. Instead of spewing molten rock and ash, a cryovolcano erupts with water, ammonia, or methane. On the small, brilliant white moon of Enceladus orbiting Saturn, this process creates one of the solar system's most breathtaking sights. Gigantic plumes of water vapor and ice crystals blast from deep fissures near its south pole, shooting hundreds of miles into space. These are not mere geysers. They are ongoing eruptions fed by a global subsurface saltwater ocean that interacts with a warm, rocky core. The plumes are so powerful they contribute material to one of Saturn's iconic rings. This means a spacecraft flying through those plumes, like the Cassini probe did, can essentially taste the contents of an alien ocean without ever landing. The implications are profound. Here, in the deep freeze of space, a moon is actively venting the ingredients for life, water, organic molecules, and a source of chemical energy directly into the void. Jupiter's moon Europa presents a similar, if more subtle, picture. Its surface is a cracked and jumbled landscape of ice, suggesting a vast global ocean lies beneath. While we have not yet witnessed a plume as dramatic as Enceladus's, scientists have detected evidence of sporadic water vapor venting from its icy shell. The driving idea is the same: a hidden, warm, salty sea, possibly twice the volume of Earth's oceans, sealed under an icy lid but occasionally bursting through. These cryovolcanos rewrite the rules of where to look for habitable environments. They tell us that life does not require a sun-drenched rocky planet. It might just need a stable source of heat, liquid water, and chemistry, all of which can exist in the eternal night beneath a shell of ice, with volcanoes of water as its only clue to the universe. Hidden oceans offer a whisper of potential life, but at the very center of our own galaxy, a monstrous silence reigns. This is Sagittarius, a star, the supermassive black hole anchoring the Milky Way. Its existence is not a violent spectacle of consumption, but a profound demonstration of gravity's absolute authority. Packed into a point of infinite density called a singularity, with a mass over 4 million times that of our Sun, it warps the space around it into a bottomless pit. The point of no return is its event horizon, a spherical boundary from which not even light can escape. Crossing it would be a one-way trip into physics itself breaking down. But the approach would be even more gruesome. An object falling in would experience spaghettification, a tidal force so severe that the pull on your feet would be exponentially stronger than the pull on your head. You would be stretched into a long, thin strand of atoms before being shredded entirely. This terrifying fate awaits anything that ventures too close. Yet, just outside this zone of annihilation, we witness a frenetic celestial ballet. Stars, like the one known as S2, are whipped around this gravitational monster at speeds exceeding 15 million miles per hour. They complete an orbit in just 16 Earth years, tracing elliptical paths that come perilously close to the abyss. This frantic dance, observed for decades by astronomers, is how we confirmed the black hole's presence and measured its incredible mass. It is a place where space and time are curved beyond recognition, where the most fundamental rules of the universe are dictated by a dark, silent heart. While the black hole's heart is a silent maw, its influence can spark unbelievable violence nearby. Just look at Jupiter's moon Io, a world that endures a relentless, invisible assault. This is the most volcanically active place in our entire solar system, a landscape constantly remade by hundreds of erupting volcanoes, but its geological fury is just one part of the story. Io orbits deep within Jupiter's immense magnetic field, a region filled with charged particles trapped in deadly radiation belts. This moon is essentially swimming in a toxic bath of electrons and ions, a level of radiation so intense it would deliver a lethal dose to an unshielded human in under an hour. This invisible rain doesn't just pass through, it fundamentally alters the moon itself. The radiation constantly blasts the surface, breaking apart molecules in Io's thin sulfur dioxide atmosphere and in the colorful compounds on its ground. This process, called radiolysis, acts like a cosmic paintbrush. It helps create the moon's stunning and chaotic palette of yellows, oranges, reds, and whites, colors that come from various allotropes or forms of sulfur and sulfurous salts. Think of it as a world being simultaneously scorched by radiation and painted by it. The radiation also interacts with the volcanic plumes. When those great eruptions spew gas and dust hundreds of miles high, some of that material gets ionized by the radiation, captured by Jupiter's magnetic field and swept away. This creates a giant, donut-shaped cloud of charged particles that follows Io in its orbit, a permanent, radioactive halo born from its suffering. So Io lives a double life, tortured from within by the gravitational tug of Jupiter that heats its core and drives its volcanoes, and bombarded from without by a shroud of poison that both kills and colors it. It is a world caught in the crossfire of its own star system, a vivid testament to how a planet's embrace can be both creative and utterly annihilating. Io's radiation-blasted surface is a testament to celestial violence, but another moon in the Saturnian system offers a vision of profound, frozen calm. Titan is a world shrouded in an opaque orange haze, a place where the familiar rules of geology are rewritten in ice and liquid gas. This is the only moon in our solar system with a substantial atmosphere, a thick blanket of nitrogen even denser than Earth's own air. The surface temperature here is a cryogenic -290 degrees Fahrenheit, so cold that water ice is as hard as granite, but on Titan, water ice is the bedrock. And flowing across that frozen bedrock are rivers, lakes, and even seas of liquid methane and ethane. Imagine standing on the shore of one of these alien bodies of liquid. The ground underfoot would be a strange, solid ice rock. The liquid before you would be as clear as gin, but it would be profoundly different. Methane on our world is a flammable gas. Here in the deep freeze, it condenses into a flowing liquid. A hydrocarbon rain falls from the hazy sky, carves channels into the water ice landscape, fills vast basins, and then slowly evaporates back into the atmosphere, completing a cycle eerily similar to Earth's own water cycle. We have seen, through the eyes of the Cassini spacecraft and its Huygens lander, coastlines, deltas, and islands in these methane seas. Titan is in every sense a bizarro world version of Earth. It possesses the only other active, complex hydrological cycle we have found, but it is built from chemistry that, to us, is the stuff of natural gas and laboratory solvents. It is a frigid hydrocarbon mirror of our own blue planet, proving that the processes that shape worlds are universal, even when the ingredients are utterly alien. Titan's methane seas exist in a deep, cold calm, but our own star is a constant reminder that cosmic serenity is fleeting. The sun is not a placid ball of light. It is a churning, dynamic sphere of plasma, and its most violent tantrums can reach across the solar system. These are coronal mass ejections, or CMEs. Picture the sun's outer atmosphere, the corona, suddenly convulsing. Tangled magnetic field lines snap and reconnect, releasing energy equivalent to millions of hydrogen bombs in an instant. This explosion doesn't just release light, it hurls a colossal piece of the sun itself into space. A typical CME is a billion-ton cloud of magnetized solar plasma, a seething soup of protons and electrons launched at speeds that can exceed several million miles per hour. The scale is almost incomprehensible. If you could stand on the sun's surface as one erupted, you would witness a structure larger than many planets billowing outward, a tsunami of fire on a stellar scale. The environment within that cloud is a realm of pure, chaotic fury. It is a storm of high-energy particles, all trapped and guided by snarled magnetic fields that twist and turn. Any spacecraft caught in its path would be bombarded by radiation intense enough to fry unshielded electronics and pose a severe risk to astronauts. But the true danger of a CME lies not in the cloud itself, but in what happens when it arrives at a world like ours. When that magnetized tsunami slams into Earth's protective magnetic bubble, our magnetosphere, the results can be spectacular and devastating. The impact compresses our magnetic field on the day side and stretches it into a long tail on the night side, funneling charged particles toward the poles. This creates the breathtaking auroras, the northern and southern lights. Yet this beautiful display is a symptom of a planetary-scale electrical disturbance. The real threat is to the technology we depend on. The rapid shifts in the magnetic field can induce enormous currents in long power lines, potentially overloading transformers and causing continent-wide blackouts. It can cripple satellites, disrupting global communications, GPS, and weather monitoring. In 1859, a historic solar storm, now called the Carrington Event, caused telegraph systems worldwide to fail, with operators receiving shocks and papers catching fire from the induced currents. A storm of that magnitude today, in our far more electrified and connected world, could cause trillions of dollars in damage and take years to recover from. A coronal mass ejection is the sun reminding us of its raw, untamed power, a billion-ton warning shot fired across 93 million miles of void. That billion-ton warning shot from the sun is a fleeting fury, but one storm in our solar system has raged for centuries without pause. Jupiter's Great Red Spot is not merely a storm, it is a monument to atmospheric violence. This swirling crimson eye has been observed in Jupiter's cloud tops for at least 350 years, a hurricane so vast that our entire planet Earth could fit comfortably inside its boundaries. The environment within this perpetual tempest is a realm of unimaginable chaos. The winds scream at speeds exceeding 400 miles per hour, far beyond the sound barrier here on Earth. These are not winds that howl, they are supersonic rivers of gas tearing through an atmosphere made mostly of hydrogen and helium. The storm itself is a colossal anticyclone, a high-pressure system where the air is actually descending at its core, while the outer bands spin in a fierce counterclockwise vortex. This creates a layered hell. The reddish clouds we see are likely the highest, coldest layers of the storm, possibly colored by complex chemicals like sulfur or phosphorus being dredged up from deeper within Jupiter's atmosphere. As you descend hypothetically into the spot, the pressure builds to thousands of times Earth sea level, and temperatures shift dramatically. The sheer energy required to sustain such a system for centuries is staggering. It draws its power from the heat welling up from Jupiter's interior and the planet's incredibly rapid rotation, a day lasting just 10 hours. This whips the entire atmosphere into a banded frenzy of jet streams, and the Great Red Spot is an island of organized fury within that global turbulence. It is a storm that eats smaller storms, a vortex that has witnessed the rise and fall of human empires while churning, unchanged, in an alien sky. It is less a weather event and more a permanent feature of a world where the atmosphere itself is an ocean of chaos. The Great Red Spot is a storm of unimaginable scale, yet it exists within a planetary atmosphere. Venture beyond the last whispers of a star's warmth, and you will find a cold so profound it defines the very baseline of reality. This is the interstellar medium, the vast, near-perfect vacuum between the stars. Here, the concept of cold takes on a cosmic meaning. The temperature is set by the faint afterglow of the Big Bang itself, the cosmic microwave background radiation that permeates all of space. This remnant heat from the birth of the universe has cooled to just 2.7 Kelvin, which is about 455 degrees below 0 Fahrenheit. This is not merely cold, it is the universe's default setting, the ultimate chill against which all other temperatures are measured. The emptiness here is absolute. While we think of space as empty, a cubic centimeter of air at sea level on Earth contains about 10 quintillion molecules. In the best laboratory vacuums we can create, there are still billions. But in the interstellar void, that same cubic centimeter might hold only a single atom, or sometimes just a few. Atoms are literally meters apart, lonely travelers in an immense dark. This creates an environment where the very idea of temperature becomes strange. Temperature measures the jiggling motion of particles, but with so few particles, there is almost nothing to jiggle. More critically, heat cannot transfer in any way we find familiar. There is no air to conduct it, too few particles to convect it, and with distances so vast, radiant heat loss is achingly slow. An object adrift here would not feel a biting wind, it would feel nothing at all. Its own heat would slowly bleed away as infrared radiation over eons, but it would never truly equilibrate with its surroundings because there are no surroundings to speak of. For any hypothetical interstellar traveler, this is the ultimate deep freeze and the ultimate insulation. A ship's hull would face the paradox of trying to shed excess heat from its reactors and crew into a void that cannot accept it, while simultaneously being surrounded by a cold that is almost impossible to physically touch. It is a silent, still, and nearly perfect emptiness, the universe's most pristine and inhospitable frontier. Yet even the coldest void can serve as the birthplace for stellar infernos. Far beyond the sparse reaches of interstellar space, within a satellite galaxy of our own, a region exists where star formation is not a delicate process but a cataclysmic explosion of creation. This is the Tarantula Nebula, a sprawling cloud of gas and dust located in the Large Magellanic Cloud, about 160,000 light-years away. It earns its name from its spidery, filamentary tendrils of glowing gas, but this is no delicate web. It is the most active stellar nursery in our entire local group of galaxies, a hyperstellar factory operating at a frenzied, almost violent pace. At its heart lies a mammoth cluster of newborn stars called R136, a cosmic powerhouse containing some of the most massive and luminous stars ever catalogued. These are not stars like our Sun. They are behemoths, many weighing over 100 times the mass of our own star, and they burn with a ferocious blue-white intensity. Their brilliance is so extreme that if you place the Tarantula Nebula at the distance of the Orion Nebula, the nearest stellar nursery to Earth, it would cast shadows on our planet at night and be visible as a glowing patch even during the day. The environment within this nebula is shaped by these stellar titans. They flood their surroundings with an onslaught of ultraviolet radiation so powerful it ionizes the surrounding hydrogen gas, causing it to glow with an ethereal red hue. But they also unleash torrents of charged particles, stellar winds that scream outward at millions of miles per hour. These winds act like cosmic sandblasters, carving vast cavities and sculpting the nebula's intricate pillars and ridges. The pressure from this radiation and these winds compresses nearby clouds of gas, triggering further collapses and igniting yet more stars in a relentless chain reaction. Here, stars are born not in quiet isolation, but in a roaring, radiant tempest, their very formation fueled by the fury of their colossal siblings. It is a place where the life cycle of stars is displayed in its most dramatic, explosive, and beautiful form. The Tarantula Nebula's stellar furnaces are powerful, but their energy is dwarfed by engines operating at the very hearts of galaxies. When a supermassive black hole is not just a silent predator but an active, feeding beast, it can unleash the most powerful sustained eruptions in the known universe. These are the relativistic jets of active galactic nuclei. In galaxies with such a hungry central black hole, immense amounts of gas, dust, and even entire stars spiral inward, forming a superheated, whirling disk of plasma. But not all this doomed material falls past the event horizon. Through processes still not fully understood, a fraction of it gets channeled and focused by the black hole's immense spin and magnetic fields. The result is a pair of beams shot directly from the poles of the system, moving at over 99% the speed of light. These are not gentle streams. They are tsunamis of charged particles blasted across intergalactic space. Their scale is utterly incomprehensible. A single jet can stretch for hundreds of thousands of light years, far beyond the boundaries of its host galaxy itself, piercing the intergalactic medium like a cosmic searchlight. The environment inside one of these jets is a realm of physics pushed to its absolute limit. Individual protons and electrons are accelerated to energies billions of times greater than anything produced in our most powerful particle colliders. They spiral along magnetic fields of unimaginable strength, fields that are trillions of times more powerful than Earth's. This chaotic, high-energy maelstrom generates radiation across the entire spectrum, from long radio waves to the most penetrating gamma rays. If a star system were to somehow find itself in the path of such a jet, it would be an extinction event of galactic proportions. The planet's atmosphere would be stripped away, its surface sterilized by the relentless blast of radiation and particles. These jets are the universe's ultimate particle accelerators, natural engines of destruction and creation that shape the evolution of galaxies and carve vast cavities in the clusters of galaxies they inhabit. They remind us that the core of a galaxy is not always a quiet place of old stars, but can be the site of a violence so profound it echoes across cosmic distances. Relativistic jets reshape galaxies, but the engines that launch them often begin with a star's self-annihilation. When a massive star exhausts its nuclear fuel, its core collapses in a cataclysm called a supernova. The outer layers blast away in a brilliant explosion visible across galaxies, but what remains behind is a cosmic tombstone of impossible density, a neutron star. This is the collapsed core, a sphere only about 12 miles across, yet containing more mass than our entire sun. All that matter is crushed into a state so extreme that atoms themselves cannot exist. Electrons are forced into atomic nuclei, merging with protons to form a solid sea of neutrons. The density is beyond human scale. A single teaspoon of neutron star material would weigh about 10 million tons, the mass of a large mountain compressed into a tiny scoop. This creates a surface environment that is the definition of physical extremity. The gravity here is about 100 billion times stronger than Earth's. If you could somehow hover just a meter above this surface and drop a marble, it would strike the ground at over half the speed of light. The impact would release the energy of a nuclear bomb. The surface itself is not like any ground we know. It is thought to be a crystalline crust of iron nuclei, packed into a perfect lattice so tight it resembles a single, immense atomic nucleus. But even this solid is an illusion of scale. The crust is likely only about 1 kilometer thick, a brittle shell over an ocean of superfluid neutrons that flow without any friction. And then there are the magnetic fields. A neutron star born from a rapidly spinning progenitor can have a magnetic field 1 trillion times stronger than Earth's. This field is so powerful it is not an invisible force but a tangible environment. It would warp the electron clouds of any atom brought near it, ripping molecules apart and polarizing matter on a subatomic level. A human or any spacecraft approaching this surface would be spaghettified by gravity long before arrival, and then its very atoms would be torn into a stream of particles aligned by the magnetic field. A neutron star is not a place, it is a state of matter, a warning written in gravity and spin about the ultimate fate of crushed starlight. From the crushing density of a neutron star, we travel back to the very beginning of a solar system's story. Around a newborn star, a different kind of cosmic chaos unfolds. This is the protoplanetary disk, a vast, swirling platter of gas and dust that serves as the raw construction site for planets. Picture a star like our own sun in its infancy, blazing to life at the center of a collapsing cloud. The material that doesn't fall into the star itself gets spun out into a flattened disk, a celestial whirlpool that can stretch for billions of miles. The environment here is not serene. It is a churning, dusty maelstrom. Tiny grains of silicate rock and ice, finer than smoke, are caught in a violent ballet. They orbit the young star, but they also constantly collide. At these slow, initial speeds, they don't shatter. Instead, they stick together through static forces, a process called accretion. Dust clumps become pebbles, pebbles become boulders, and boulders grow into mountain-sized bodies called planetesimals. This is the foundational stage of planet building, a game of cosmic bumper cars played over millions of years. The violence escalates as these planetesimals grow. Their own gravitational pull begins to influence the disk, clearing paths in the dust and gas as they sweep up more material. This is how we can spot these nurseries from Earth. When astronomers look at a star like HL Tauri, they don't see the planets directly. Instead, they see a stunning series of dark, concentric rings in the glowing disk. Those rings are the lanes cleared by infant protoplanets, cosmic snowplows carving out their future orbits. It is a dusty, dynamic, and profoundly violent construction zone, where the gentle worlds we know are forged from endless, grinding collisions under the harsh light of a young sun. Those planetesimals are the seeds of worlds, but what determines where they will grow? To find that answer, we must pull back, far back, until entire galaxies look like specks of dust. At this grandest scale, the universe reveals its underlying architecture, a structure so vast it makes the Tarantula Nebula seem like a tiny spark. This is the cosmic web. It is not made of stars or glowing gas, but of something far more mysterious and dominant: dark matter. Picture the universe not as a random scatter of galaxies, but as an immense, three-dimensional spiderweb. The thick knots where the strands intersect are the great clusters of galaxies, containing thousands of individual islands of stars. But the true marvel are the strands themselves, the filaments. These are unimaginably long, thin rivers of dark matter and trace amounts of hydrogen gas, stretching for hundreds of millions of light years across the void. They form a scaffolding, a skeleton upon which the visible universe is draped. This is the single most massive structure in all of existence. The environment within one of these filaments is one of profound emptiness and overwhelming gravity. While a galaxy cluster is a crowded metropolis, a filament is a lonely cosmic highway. The density of matter here is still far, far less than in a galaxy, but it is markedly higher than in the terrifying voids like Boötes. This slight over-density is everything. It means the gravity here is a fraction stronger, just enough to act as a conduit, a gravitational channel that guides ordinary matter, the gas that will form stars and galaxies, flowing along its length toward the dense clusters at the intersections. We cannot see the dark matter filaments directly as they emit no light, but we can see their influence. Astronomers map the positions of millions of galaxies and find they are not randomly placed. They trace out these filamentary patterns, clinging to the invisible scaffold like dew on a web. We can also detect the faint glow of hydrogen gas that has been heated and illuminated as it falls along these cosmic rivers into the waiting galaxy clusters. So while you could fly a spaceship through a filament and see almost nothing with your eyes, you would be moving through the universe's foundational framework, traveling along a highway of gravity built by the unseen majority of all that exists. It is the ultimate reminder that what shapes our cosmos is not the glittering lights we see, but the hidden architecture we can only infer. That hidden cosmic scaffold shapes grand structures, but gravity's power is equally terrifying up close. Every large celestial body, like a planet or a star, holds a zone of absolute gravitational dominance called the Roche limit. This is not a physical barrier you can see, but a mathematical line of doom. It is the critical distance within which the tidal forces from a larger object become stronger than the self-gravity holding a smaller one together. Think of it this way. A moon is held in one piece by its own internal gravity, the mutual attraction of all its rock and dust. But if that moon drifts too close to its planet, the planet's gravity begins to pull more forcefully on the near side of the moon than on its far side. This difference in pull is a tidal force, and it acts like a relentless stretching hand. For a solid, rocky moon, crossing the Roche limit means it will experience stresses greater than its own structural integrity. It will begin to crack and fracture from the outside in. For a loosely held together body, like a comet or a rubble pile asteroid, the process is even more dramatic. The object doesn't even need to be solid to cross the line. As it passes within the Roche limit, the tidal forces overcome the feeble gravity that was holding its collection of boulders and dust together. The asteroid stops being a single object. Instead, it becomes a stream of individual particles, all suddenly freed from each other and forced to follow their own independent orbits around the planet. This is a slow-motion disintegration, a gravitational shredding that can take hours or days to complete. We see the aftermath of such events in the most stunning planetary features in our solar system. Saturn's magnificent rings are the classic example. Astronomers believe they are the remnants of a moon, perhaps as large as our own, that wandered within Saturn's Roche limit and was torn apart. The countless ice and rock fragments, unable to reassemble into a moon, now spread out into a vast flat disk, a permanent celestial graveyard marking the boundary where a world ends and a spectacle begins. For any spacecraft or astronaut, crossing a Roche limit would be a silent, inescapable catastrophe. There would be no violent impact, just an increasing sense of unease as the very ground beneath you began to tremble and pull apart, as boulders the size of houses slowly drifted away from each other into the void before the planet's gravity took each piece on a final, separate journey. It is gravity not as a binding force, but as a meticulous, unstoppable dissolver of worlds. Jupiter's gravitational shredding is a silent process, but its polar skies scream with light. The auroras that crown this giant are not the gentle, dancing curtains we see on Earth. They are permanent, ferocious storms of radiation, hundreds of times more energetic and larger than our entire planet. These are not driven by the solar wind alone. Jupiter possesses the most powerful planetary magnetic field in our solar system, a vast, invisible bubble that traps and accelerates charged particles to incredible speeds. One primary source of this fuel is its own tortured moon, Io. The relentless volcanic eruptions on Io spew out sulfur and oxygen atoms, which become ionized by Jupiter's intense radiation belt. These charged particles are then swept up by the magnetic field and funneled at nearly the speed of light down into the planet's upper atmosphere at the poles. When these high-energy projectiles slam into the hydrogen-rich air, they do not just create visible light. They generate a furious glow across the electromagnetic spectrum, from ultraviolet to lethal X-rays. The result is a pair of continuous, swirling halos of energy, each one larger than Earth, blazing above the poles. If human eyes could see in ultraviolet or X-ray light, Jupiter would not appear as a striped gas ball, but as a world crowned with two searing, planet-sized rings of fire, a constant testament to the violent electromagnetic furnace churning within. This is not a nightly display, it is a perpetual state of being, the visible signature of a magnetic engine so powerful it turns a moon's volcanic exhaust into a celestial light show of terrifying scale. Jupiter's permanent auroras are fueled by a moon's volcanic exhaust, but some planets are the source of their own destruction. Orbiting a sun-like star 150 light-years away is a world named HD 209458b, nicknamed Osiris. This is a hot Jupiter, a gas giant locked in a blisteringly close embrace with its star, completing an orbit in just 3.5 Earth days. That proximity creates a stellar furnace, heating the planet's outer atmosphere to a staggering 18,000 degrees Fahrenheit. At that temperature, the hydrogen gas in the upper atmosphere doesn't just get hot, it gets frantic. The molecules move so fast they achieve escape velocity, breaking free from the planet's weakened gravity entirely. But they do not simply drift away. The intense stellar wind from the parent star catches this stream of liberated gas, blowing it backward into space. The result is a planetary-scale comet tail. Osiris is literally evaporating, leaving a gigantic, streaming plume of hydrogen and other gases that stretches over 200,000 kilometers behind it. This is not a temporary event or a gentle leak. It is a continuous, catastrophic loss. Astronomers estimate this world is losing over 10,000 tons of its atmosphere every second. Imagine standing on a hypothetical platform on the night side of this doomed planet, looking up. You wouldn't see a starry sky, but a vast, glowing nebula of the planet's own stripped-away atmosphere, illuminated by the fierce light of the nearby star. The solar wind would howl past at millions of miles per hour, a constant, silent hurricane tearing the very air from the world. This is an environment defined by erosion on a cosmic scale, a place where a planet's atmosphere is not a protective blanket, but a temporary shroud being violently blown into the void. Osiris shows us a planet in its death throes, slowly transforming from a gas giant into a bare, rocky core over billions of years, its essence scattering into the interstellar dark. A planet's slow evaporation is a drawn-out tragedy, but the universe can also deliver a single, instantaneous verdict of extinction. Gamma-ray bursts are the most powerful explosions known to exist, capable of outshining entire galaxies for a fleeting moment. While the burst itself is a blinding flash of high-energy photons, the true environmental horror lies in the aftermath it leaves behind. The burst is thought to be the birth cry of a black hole, the final collapse of a massive, rapidly spinning star, or the cataclysmic merger of two neutron stars. In that instant, it unleashes focused beams of radiation trillions of times more energetic than visible light. Any planetary system unfortunate enough to lie within the narrow path of one of these beams would experience an apocalypse in seconds. The initial gamma-ray flash would deliver, in less time than it takes to blink, a radiation dose millions of times greater than a lethal amount. It would act like a cosmic flashbulb, instantly ionizing the upper atmosphere of any world in its line of sight. But the devastation is just beginning. The afterglow of the burst, a lingering soup of X-rays and ultraviolet radiation, would persist for days or even months. This prolonged assault would chemically transform the atmosphere, breaking down protective ozone and complex molecules like nitrogen and oxygen. It would trigger a cascade of chemical reactions, generating vast blankets of toxic brown nitrogen dioxide, smothering the skies in a poisonous haze. The high-energy particles would then strip away the atmosphere itself, molecule by molecule, blasting it into space. Within a year, a once blue, life-bearing world could be reduced to a barren, airless rock, its surface bathed in lethal ultraviolet radiation from its own star, now unopposed. The region of space for light years around the burst becomes a sterilized cavity, a cosmic dead zone. Any emerging life or complex chemistry within that volume is simply erased. It is a sobering thought that a random, silent flash from a galaxy billions of light years away, if pointed directly at us, could represent the ultimate environmental reset button for our planet. The universe reserves this power not for malice, but as a simple byproduct of its most violent physics. That silent, sterilizing flash from a gamma-ray burst is a universe-spanning threat, but our own cosmic backyard holds a world sculpted by a cold so deep it feels eternal. Beyond Neptune, in the dark, icy reaches of the Kuiper belt, Pluto orbits in a perpetual, slow-motion winter. The data and images from the New Horizons flyby revealed a landscape of breathtaking and alien beauty, a testament to geology performed at temperatures near 400 degrees below zero. Here, water ice is not a liquid or a vapor, it is the bedrock as hard as granite. Towering mountains of this water ice rise for miles, their peaks capped with exotic snows of methane. But the real action happens on the vast plain known as Sputnik Planitia. This is a sprawling glacier, but not one made of water ice. It is a sea of solid nitrogen, flowing with an almost ghostly slowness over eons. And drifting on this frozen, viscous sea are icebergs. These are not icebergs of water, but of methane ice, chunks that have broken off from the surrounding highlands. The physics at play here is a delicate dance of density and temperature. At Pluto's cryogenic extremes, solid nitrogen is actually less dense than solid methane. This means the methane icebergs, though still incredibly cold and hard, are buoyant. They float on the denser, softer nitrogen ice like cubes in a slow-motion cocktail. The entire process unfolds with a patience that defies human perception. The nitrogen ice itself convects, with warmer blobs slowly rising from below in a cycle that may take hundreds of thousands of years, constantly resurfacing the plain and jostling the icebergs in a sluggish geological waltz. This is a world where the very ground you stand on is a flowing solid, where mountains are made of water ice rock, and where icebergs of one frozen gas sail silently across a sea of another. It is a realm of profound stillness and cold, where the most dramatic geological events happen in a time frame that makes mountains seem ephemeral. Pluto's slow-motion icebergs drift in a profound quiet, but across the cosmic web, gravity can create a different kind of distortion, one that warps reality itself. A galaxy cluster is not just a crowd of stars, it is the universe's most powerful natural telescope. Take Able 370, a colossal congregation of hundreds of galaxies located about 5 billion light-years away. The combined mass of all those stars, planets, and gas is staggering, but it is the invisible component, the dark matter, that truly dominates. This immense concentration of mass warps the very fabric of spacetime around it, creating a gravitational well so deep it bends the path of light passing nearby. The cluster becomes a lens, a cosmic cauldron of optics. Light from even more distant galaxies, traveling for billions of years from behind the cluster, does not travel in a straight line as it approaches. Instead, it is forced to curve around this gravitational obstacle. To our telescopes, this creates a spectacular illusion. The distant galaxies appear not as they are, but as stretched, magnified, and often duplicated into arcs and smears of light like reflections in a funhouse mirror. The most famous example from Able 370 is the Dragon, a single background galaxy warped into multiple, elongated images that resemble a mythical beast. But the environment at the very heart of this lens is a maelstrom. Here, the dark matter weaves its gravitational web, while the space between galaxies is filled with a seething plasma, gas heated to millions of degrees by the violent motions of the cluster's members. This hot gas emits powerful X-rays, revealing a caustic, energetic environment. Hundreds of individual galaxies, each with billions of stars, whip through this soup, their own gravity adding tiny ripples and knots to the overall warp. It is a chaotic gravitational orchestra with every component, seen and unseen, contributing to the final, twisted image we receive. This lens does more than create a beautiful picture. It acts as a natural magnifying glass, allowing us to see galaxies so faint and distant they would otherwise be utterly invisible. We are peering at the infant universe, using the warped spacetime of a cosmic titan as our lens. That cold, slow-motion world of floating icebergs could not be more different from the next destination. HD 189733b is a deep, royal blue dot against the black of space, a color that from a distance suggests a serene ocean world. This illusion shatters the moment you draw near. This is a hot Jupiter, a gas giant orbiting so close to its star that its atmosphere is a superheated, churning hellscape. The temperature on its day side soars to nearly 2,000 degrees Fahrenheit, hot enough to melt aluminum. But the true horror is not the heat alone, it is what the heat sets in motion. The planet's atmosphere is laced with silicate particles, the same fine dust that makes up sand and glass on Earth. At these temperatures, those silicates do not lie dormant. They vaporize, becoming a shimmering, microscopic fog suspended in the air, and then the wind begins. The extreme temperature difference between the planet's permanent day and night sides drives atmospheric currents of unimaginable ferocity. These are not winds as we know them. They are supersonic rivers of scorching gas and silicate screaming across the planet at speeds exceeding 5,000 miles per hour. That is over 7 times the speed of sound here on Earth. At such velocities, the vaporized silicates are whipped into a frenzied, abrasive storm. As these particles are blown from the day side into the slightly cooler twilight of the terminator, they begin to condense. But they do not form gentle clouds. Instead, they coalesce into droplets of molten glass, and then, propelled by those supersonic gales, this glass falls. It does not rain down, it rains sideways. The planet is engulfed in a perpetual, scorching hyperstorm where the sky is a blasting sandstorm of molten silica, a horizontal hail of liquid glass that scours everything in its path. The beautiful blue color we see from afar is likely the result of this silicate haze scattering the star's blue light, a cruel cosmic irony. This is a world where the atmosphere itself is a weaponized industrial furnace, an environment of endless, screaming abrasion where the very concept of calm has been utterly erased. A world of screaming glass rain is a spectacle of atmospheric violence, but some stellar corpses wield a force far more fundamental and invisible. Deep within our galaxy, perhaps only a few dozen of the most extreme objects in existence lie in wait. These are magnetars, a rare and terrifying breed of neutron star. Remember, a neutron star is already the collapsed core of a dead star, a city-sized sphere of unimaginable density. A magnetar takes that insanity and magnifies it 1,000-fold. It possesses a magnetic field that is the strongest known force of its kind in the universe, a quadrillion times more powerful than Earth's own protective shield. To grasp that scale, consider this. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would be strong enough to erase the data from every credit card on our planet. But the true environment near one is a realm where physics as we know it breaks down. From thousands of miles away, long before any physical object could be torn apart by gravity, the magnetic field would begin its work. It is so potent it can distort the very electron clouds surrounding atoms, warping their shape and ripping molecules apart from a distance. This field is not a passive force. It is under immense stress, locked into the crust of the star, which is a crystalline lattice of iron under unimaginable pressure. This crust can crack. When it does, the event is called a starquake. It is not a tremor of rock, but a cataclysm on a stellar scale. The crust shifts, perhaps by just a centimeter, but that tiny movement in an object so dense releases more energy than our sun emits in 100,000 years. All that energy erupts in a blinding flash of gamma rays and X-rays. In 2004, a magnetar named SGR 1806-20, located 50,000 light-years away in the constellation Sagittarius, had such a starquake. For 1/10 of a second, its gamma-ray flare was brighter than the full moon, outshining every other source of gamma rays in the sky, including our own sun. The blast of energy was so powerful it actually ionized the upper layers of Earth's atmosphere, affecting long-range radio communications. This was an event from clear across the galaxy, a magnetic scream so loud it briefly touched our world. A magnetar is not just a dead star, it is a coiled spring of magnetic fury, a reminder that some of the universe's most dangerous forces are utterly silent until they are not. A magnetar's silent scream is a universe-spanning force, but on a far smaller scale. A different kind of cosmic lock creates a world of absolute contrast. Some planets become prisoners of their own stars, caught in a gravitational embrace so tight they stop rotating entirely. This is tidal locking, where one hemisphere forever faces the blazing sun and the other is cast into eternal night. The environment this creates is a study in planetary extremes. The day side is a permanent furnace, its surface baked to temperatures that can vaporize rock and metals, its atmosphere, if it has one, superheated into a roaring, expanding storm. The night side, meanwhile, is a deep freeze so profound that any atmosphere there would condense and fall as snow, creating a frozen wasteland where even gases become glacial. But between these two hellscapes lies a fragile ribbon of possibility, the Terminator line. This is the perpetual twilight zone, the narrow band where the star forever sits on the horizon. Here, the conditions could be just right. On a world with a thick enough atmosphere, heat from the day side could be transported by winds and moderated, while the cold of the night is held at bay. In this band of eternal sunrise or sunset, temperatures might settle into a range where liquid water could pool on the surface. It is a bizarre thought, a planet where life, if it could exist at all, would be confined to a single, sweeping belt around the entire world. You could walk from a blazing desert into an icy tundra simply by heading toward the sun or away from it. The sky would be a perpetual dawn or dusk, with the star forever fixed in place, neither rising nor setting. Any civilization emerging there would have a cosmology utterly alien to our own, with the concepts of day, night, and seasons replaced by geography. Their entire world would be a journey along a razor's edge, a narrow strip of moderation bordered by infinities of fire and ice. That fragile ribbon of twilight is a world of moderation, but on our neighboring planet, the entire globe can be swallowed by a single planet-wide tantrum. Mars is famous for its thin, cold air and rust-colored deserts, but occasionally that stillness erupts into a phenomenon of staggering scale, a global dust storm. These are not mere desert gusts. They begin as local tempests, often in the southern hemisphere during Mars's summer, when solar heating is most intense. Winds lift the fine, iron oxide dust from the surface, and under the right conditions, this storm acts as a seed. The suspended dust absorbs sunlight, heating the atmosphere around it. This warm air rises, sucking in more air from surrounding regions and pulling yet more dust aloft. It is a vicious, self-fueling cycle. The storm can grow from a regional haze to a planetary shroud in a matter of weeks, until the entire face of Mars is obscured beneath a tan, featureless veil. From orbit, the polar ice caps and dark surface features simply vanish. The storm rages for months, a slow-motion hurricane of dust so fine it behaves almost like a liquid, flowing over mountains and filling valleys. The environmental effects are profound. With sunlight blocked, surface temperatures can plummet by more than 30 degrees. The rovers on the ground, like Opportunity, are forced into a silent, energy-conserving hibernation, their solar panels rendered useless under the dim, ochre sky. The dust itself is more than an inconvenience. It is a fine, abrasive powder that infiltrates every seam and joint. It coats instruments, grinds at moving parts, and stains lenses. For any future human explorers, a global dust storm would be a months-long lockdown. The sky would darken to a perpetual, eerie twilight. Outside work would cease as the abrasive grit scoured suits and machinery, and solar power would crash, forcing a reliance on nuclear generators. These storms are the ultimate expression of Mars's arid, desert heart, a reminder that even a world with an atmosphere 1% as thick as Earth's can muster a weather event that envelops an entire planet, turning a cold desert into a colder, darker, and utterly dust-choked one. While Mars can be shrouded in its own dust, a far larger and more diffuse cloud is on a collision course with our entire galaxy. This is Smith's Cloud, a colossal river of hydrogen gas over 11,000 light-years long and 2,500 light-years wide. Discovered in the 1960s by astronomy student Gail Smith, it is not a cloud in the sense of water vapor, but a massive structure of mostly neutral hydrogen, the fundamental fuel for stars. What makes it extreme is its trajectory and speed. It is hurtling toward the Milky Way's disk at nearly 700,000 miles per hour, and it is not just passing by. It is destined to strike. Astronomers have traced its path backward through time, and the evidence suggests a dramatic origin. This cloud was likely ejected from the outer regions of our own galaxy, perhaps ripped away by a close encounter with a dwarf galaxy, or launched by a series of supernova explosions millions of years ago. It has spent eons on a giant, arcing loop through the galactic halo, the sparse spherical region surrounding the Milky Way, and now it is coming home in the most violent way possible. The environment within Smith's Cloud is one of eerie, tenuous anticipation. If you were inside it, you would not see a dense, foggy nebula. The gas is so diffused that it is nearly a perfect vacuum by Earth standards, far emptier than even the best labs can create. You would see only the distant, distorted band of the Milky Way ahead, growing larger as you race toward it. But this faint cloud carries immense kinetic energy. In about 30 million years, it will plow directly into the spiral arm of our galaxy. The impact will be slow and colossal, not a fiery explosion, but a gravitational and pressure-driven implosion. As the cloud smashes into the denser gas of the galactic plane, it will create immense shock waves. Those waves will compress vast reservoirs of hydrogen, squeezing them until they reach the critical density needed for gravity to take over. The result will be the ignition of countless new stars, a firestorm of stellar birth sparked by a returning exile. Smith's Cloud is a celestial boomerang, a reminder that galaxies are not static islands, but dynamic ecosystems that can expel and reaccrete their own material, using the violence of a collision to seed the next generation of suns. The cold, tenuous river of Smith's Cloud is on a journey of millions of years, but in the asteroid belt, a small world holds a frozen monument to a different kind of internal fire. This is Ceres, the largest object between Mars and Jupiter, a dwarf planet that defies its rocky neighbors. For a long time, it was considered a simple, inert sphere of rock and ice. Then the Dawn spacecraft arrived, revealing a world with a surprising secret. Its surface is dotted with bright, salty deposits, but one feature stands utterly alone. A solitary mountain named Ahuna Mons rises over 13,000 feet from the plains, a peak with no geological family, no surrounding range. Its steep, gleaming sides are scarred with recent-looking streaks, and it possesses a shape unlike any other mountain in the solar system. This is not a volcano of molten rock. Ceres is too small and cold for that. Ahuna Mons is a cryovolcano, a mountain built from ice and cold mud. Deep within Ceres, scientists believe a reservoir of brine persists, a slushy mix of water, salts, and likely clay, kept liquid by the residual heat from the dwarf planet's formation and the decay of radioactive elements. This isn't a fiery magma chamber, but a cold, muddy aquifer under pressure. Occasionally, that pressure finds a weak spot in the brittle, icy crust. The frigid, briny mud forces its way to the surface, not in a violent explosion, but in a slow, viscous ooze. It piles up layer upon frozen layer, building a mountain of icy sludge over millions of years. The environment here is one of profound stillness and cold, where the landscape is shaped not by fiery tectonics, but by the sluggish flow of antifreeze. Imagine standing at the base of Ahuna Mons. The ground underfoot would be a dark, rocky ice, and the mountain itself would gleam with a bright, salty crust. There is no atmosphere to speak of, so the sky is a perfect, starry black. The silence is absolute. This lonely peak is a testament to the quiet, persistent heat hiding within even the smallest worlds, a geological oddity that proves internal fire can take the form of a slow, freezing mudslide. The lonely, frozen peak of Ahuna Mons exists in a profound and local silence, but to see a single star from across the universe requires a cosmic shout and a perfect cosmic trick. This is the story of Icarus, the most distant individual star ever seen. Its official designation is a string of numbers and letters, max J1149 plus 2223 lensed star 1, but its story is pure celestial magic. Icarus is not a galaxy, not a cluster, but a solitary blue supergiant, a massive, brilliant star shining alone in the blackness of the early universe. Its light began traveling toward us over 9 billion years ago, when the universe was only about 30% of its current age. For almost the entire history of our planet, that faint photon stream has been racing through the expanding void. By all rights, it should have remained forever invisible, a single candle lost in the glare of a city. But between Icarus and our telescopes lay a massive galaxy cluster. This cluster, like a lens of unimaginable scale, warped the spacetime around it. The star's light, as it passed by, was bent and focused. The cluster's gravity acted as a natural telescope, magnifying Icarus's faint glow by a factor of over 2,000. Suddenly, the candle became a beacon. We were not looking at the star's host galaxy, we were looking directly at the star itself, a pinpoint of ancient light stretched and duplicated by the curvature of space. The environment along that line of sight is a journey through layered cosmic history. The light from Icarus did not travel through empty space. It traversed the intergalactic medium, a sparse soup of hydrogen and helium, and passed through the outer halos of countless galaxies, each subtly dimming and reddening its journey. Then it encountered the lensing cluster, a turbulent region of hot gas, dark matter, and the distorted gravity of hundreds of galaxies. This cosmic lens did not just magnify the light, it also smeared it into a long, thin arc, a visual echo of the warped path it was forced to take. For a brief period, thanks to a perfect alignment and the natural optics of a gravitational lens, we witnessed a star that lived and died billions of years before our own sun even formed. Icarus is a ghost, its image a whisper from an era when the universe was young, made audible only because the cosmos itself provided the ultimate amplifier. The ghostly light of Icarus is a whisper from the deep past, but our first confirmed encounter with worlds beyond our sun came from a star that was already dead. In 1992, astronomers made a discovery that rewrote the textbooks. Orbiting a rapidly spinning stellar corpse known as PSRB 1257+12, they found planets. This was not a serene, sunlit system like our own. This was a graveyard solar system, the first exoplanets ever detected, and they circle a pulsar. The environment here is the definition of post-apocalyptic. The central star is a neutron star, the dense remnant of a massive sun that died in a supernova explosion. It spins hundreds of times per second, beaming out a lighthouse-like pulse of radiation with metronomic precision. It was that precision that gave the planets away. Tiny, regular variations in the timing of the radio pulses revealed the gravitational tugs of at least 3 small worlds. These planets are bathed in an unrelenting, lethal bath of X-rays and high-energy particles from the pulsar. Any atmosphere they might have once possessed would have been stripped away eons ago. What remains are likely barren, rocky cores, perhaps the shattered remnants of larger planets that survived the star's violent death, or bodies that reformed from the debris of the cataclysm. Imagine the view from the surface of one of these worlds. The sky would be dominated by a tiny, rapidly flickering point of blinding light, the pulsar casting stark, strobing shadows. There would be no warmth, only a cold so profound it seeps from the rock itself, punctuated by flashes of sterilizing radiation. It is a system born from destruction, a testament to the fact that planets can endure even the most violent stellar deaths, orbiting a tombstone that ticks with perfect, deadly rhythm. A graveyard solar system circles a silent corpse, but other worlds endure a far more active and scorching damnation. These are the lava worlds, exoplanets like Kepler-10b and Ko-Ro T7b. They are not gas giants, but dense, rocky spheres similar in composition to Earth or Venus. Yet any resemblance ends there. These planets orbit so close to their parent stars that their entire existence is defined by searing proximity. A single year on Kepler-10b, one complete orbit, lasts less than one Earth day. This blistering dance locks the planet with one hemisphere perpetually facing the stellar inferno. The dayside temperature soars beyond 2,500 degrees Fahrenheit, hotter than a blast furnace and well above the melting point of rock. What does a rocky surface become under such an onslaught? It becomes an ocean, not of water but of molten silicate rock, a global sea of lava. Picture the surface not as solid ground but as a slowly churning, incandescent expanse. There are no mountains, no valleys in any permanent sense. The landscape itself is liquid, with sluggish waves of magma driven by fierce stellar winds and the planet's own rotation. The very crust is being continuously melted from above by the star's radiation and remelted from below by the planet's internal heat, trapped and amplified by the intense gravity of its tight orbit. On the night side, the temperature might drop just enough for a thin, brittle crust to form, but it would be a fragile shell over a world of fire, constantly cracking and subducting back into the magma ocean. These are planets where geology is performed in a state of permanent liquid fury, where the concept of land is a fleeting illusion, and the sky is a canopy of blinding light from a star that fills half the heavens. Lava worlds are prisoners of their own suns, but entire clusters of galaxies may be caught in a current flowing towards something we cannot see. This is the mystery of the dark flow. Cosmologists studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed something unsettling. When they mapped the motion of massive galaxy clusters, they found a strange, coordinated drift. Hundreds of these immense structures, each containing thousands of galaxies, appeared to be moving in the same direction at incredible speeds, toward a specific point in the sky near the constellations Centaurus and Vela. This wasn't the random, gentle expansion of the universe. It was a subtle but persistent stream. The environment this implies is staggering. For something to exert a gravitational pull strong enough to tug entire galaxy clusters, it must be a structure of unimaginable mass and scale, far beyond the largest supercluster we know. But here's the truly profound part. This mysterious attractor lies beyond the edge of our observable universe. The light from it, if it emits any, has not had time to reach us since the beginning of everything. So we are left with the ghostly evidence of its pull, a shadow on the wall of our cosmic cave. What could it be? One radical possibility is a massive concentration of matter left over from the chaotic inflation of the Big Bang, a region so dense it warps spacetime on a multiversal scale. Another, even more extreme idea is that the dark flow is a gravitational tug from a neighboring universe in a vast multiverse, a separate bubble of reality brushing against our own. This isn't just a flow of galaxies. It could be a current leading to a shore we can never reach, hinting that our entire cosmos is but one island in an infinite, unseen archipelago of realities. The dark flow hints at forces beyond our cosmic horizon, but within our own solar system, a world has been knocked permanently askew. Uranus is the solar system's oddball, a serene blue ice giant spinning on its side. Its axis is tilted a staggering 98 degrees, meaning it essentially rolls around the sun like a celestial bowling ball. This extreme orientation creates a seasonal cycle of almost unimaginable duration and intensity. A single year on Uranus lasts 84 Earth years. Because of its extreme tilt for 42 of those years, one pole is pointed almost directly at the sun, while the other is cast into the blackness of space. Imagine a summer that lasts for 4 decades. On the sunlit pole, the sun would never set. It would hang, a small but brilliant point of light near the zenith of the sky, tracing tiny circles as the planet slowly rotates. This hemisphere would bake under continuous, weak sunlight for half a human lifetime. Meanwhile, the opposite pole endures a winter just as long, a deep freeze of utter darkness lasting 42 years. The temperature contrast between these two eternal realms would be staggering, driving wild atmospheric phenomena. As the planet slowly orbits, the roles reverse, and the frozen pole begins its own 4-decade-long thaw into perpetual daylight, while the previously sun-drenched hemisphere plunges into its own decades-long night. This creates a world where seasons are not measured in months, but in generations, a climate of such profound patience that its greatest changes are invisible to any individual observer. The very atmosphere must churn and roil in a slow-motion struggle to redistribute heat from the endless summer to the endless winter, a planetary-scale effort to find a balance that its own extreme tilt makes forever impossible. Even a planetary nebula, that final, gentle sigh of a dying star, can become a cosmic runaway. Normally, these glowing shells of gas mark the quiet end of a sun-like star, expanding slowly into the void as a beautiful, symmetrical cloud. But introduce a violent partner and the result is chaos in motion. Imagine a binary star system where one star reaches its end, swelling into a red giant and eventually casting off its outer layers. Its companion, however, is a white dwarf, a dense stellar cinder. If conditions are right, the white dwarf can pull too much material from its dying partner, crossing a critical mass limit and detonating in a cataclysm called a Type 1, a supernova. The explosion is so sudden and powerful it doesn't just destroy the white dwarf, it violently ejects the other star from the system entirely. The companion is flung away like a stone from a sling, but it doesn't leave empty-handed. It carries with it the glowing shroud of gas that was just expelled in the red giant phase, now caught in the blast wave. This creates a hypervelocity planetary nebula. What was once a statically expanding bubble becomes a hurtling cloud, screaming through the interstellar medium at speeds that can exceed 100,000 miles per hour. The environment around this runaway remnant is one of constant sculpting collision. The nebula is no longer floating in a quiet vacuum. It is plowing through the thin gas that exists between stars. This interaction creates a visible bow shock at its leading edge, a glowing arc of compressed and heated material, much like the wave that forms at the bow of a speeding ship. Behind it, the nebula's own gas is stretched and torn by the passage, forming a long, comet-like tail that streams across light years. From a distance, it appears as a celestial arrowhead, a beautiful and tragic smear of light pointing directly away from the site of the stellar catastrophe that birthed it. We are witnessing a funeral procession in fast forward, a ghostly shell racing to outrun its own violent past, its beautiful forms shaped not by a gentle death, but by a stellar betrayal and a frantic escape through the galactic winds. That runaway nebula flees a known catastrophe, but the oldest light in our universe holds a mark from something far stranger. Woven into the faint glow of the cosmic microwave background, the afterglow of the Big Bang itself, is an anomaly astronomers call the cold spot. This is a vast region of space, nearly 1.8 billion light-years across, that is significantly colder than the surrounding cosmic backdrop. The temperature difference is minuscule, only about 70 microkelvins, but on the smooth canvas of the early universe, it stands out like a giant, frigid bruise. One leading theory suggests it is a supervoid, an emptiness on a scale that dwarfs even the Boötes Void. In such a vast region of nothingness, with far fewer galaxies and less matter, light passing through would lose a tiny amount of energy as it climbs out of the shallow gravitational well, a process called the integrated Sachs-Wolf effect. This would make the CMB light from that direction appear slightly colder to us. Yet the sheer size of the cold spot pushes the limits of what we think is possible from random cosmic structure. This has led to a more breathtaking and far more speculative idea. Some physicists propose it could be an imprint of a collision with another universe. In the multiverse theory, our cosmos might be one bubble among infinite others in a frothing, eternal inflation. If another bubble universe brushed against ours in the distant past, the energy of that collision could have left a scar on our newborn cosmos, a circular region of cooled spacetime recorded forever in the first light. The environment this cold spot represents is not one of physical objects but of profound implication. It is a shadow on the wall of our cave, a potential fingerprint from beyond the horizon of everything we can observe. Whether it is a record-shattering void or a bruise from a cosmic clash, it serves as a humbling reminder that the extremes of our universe may not be limited to what is within it, but could be signatures of what lies forever outside. Even the Moon, our closest celestial neighbor, holds pockets of extreme contrast. At its north and south poles, the Sun hangs perpetually low on the horizon, casting long, inky shadows that never move. Yet on the high rims of certain craters, like the edge of Shackleton crater at the South Pole, the geometry creates a phenomenon called the peaks of eternal light. These are mountain ridges and crater rims angled so perfectly that they bask in sunlight for over 80% of the lunar day, nearly constantly illuminated. For a future astronaut standing on such a peak, the Sun would skim the horizon, tracing a slow, lazy circle in the black sky, but never truly setting. The ground underfoot would be a stark gray, blasted by unfiltered solar radiation, offering a nearly limitless supply of solar energy. Yet just a few kilometers away, in the deep abysses of polar craters like Shackleton's own floor, lies the opposite extreme. These are the pits of eternal darkness. Their depths are so profound and their angles so steep that sunlight has not touched them for billions of years. Temperatures there plunge to nearly 400 degrees below zero, some of the coldest places in the entire solar system. This permanent freeze is a cosmic deep freezer, and it has trapped a precious resource. Within these shadowed pits, water ice delivered by ancient comet impacts has remained preserved, untouched by the Sun's heat. This creates a surreal, microscopic-scale environment where a sun-drenched ridge and a frozen, dark abyss exist within sight of each other. For human exploration, this duality is a perfect gift. The peaks offer power, while the neighboring pits offer the water necessary for life and rocket fuel. A future lunar base could literally be built on the line between eternal light and eternal night, a foothold on another world balanced between two absolutes. Deep within the Milky Way's halo, a relic star holds a secret that upends our cosmic story. Catalogued as SDSS J102915+172927, this ancient sun is a fossil from the universe's first few 100 million years. Its composition is shockingly simple, made almost entirely of hydrogen and helium. For astronomers, the term metals refers to any element heavier than helium, the products forged in stellar furnaces and supernova explosions. Our own sun is rich with these metals, a testament to generations of stars that lived and died before it. But this star is different. Its metal content is so vanishingly low, it is over 20,000 times poorer in metals than our sun. This presents a monumental puzzle. According to our best models, the very first stars, known as population 3 stars, should have been colossal behemoths made only of hydrogen and helium. They lived fast, died young in titanic supernova, and seeded the cosmos with the first heavy elements. After that, no new stars should have been able to form without at least a trace of those metals to help gas clouds cool and collapse. Yet here is SDSS J102915+172927, a star that clearly formed after those first generations, but with almost none of their ashes. It is a star that, by our current understanding, should not exist. Its environment is one of profound purity, a solitary witness to an era before the universe was polluted with the complex elements that make planets and life possible. It hangs in the galactic halo, a pristine time capsule whose very existence forces us to reconsider the recipe for star birth in the infant cosmos. Perhaps the first stars were not all giants, or maybe some pockets of primordial gas remained untouched for longer than we thought, collapsing in quiet isolation to form rare, ancient suns like this one. It is a quiet, faint challenge written in the oldest chemistry of all. Such ancient, pristine stars exist in a slow, stately isolation, but some worlds are defined by the exact opposite principle, a frantic, dizzying spin. In the dark, icy reaches of the Kuiper belt beyond Neptune, a dwarf planet named Haumea performs a celestial pirouette of impossible speed. This is not a sphere. Haumea spins so rapidly, completing a full rotation in just 4 hours, that it cannot hold a round shape. The relentless centrifugal force has stretched it, sculpting it into a smooth, elongated ellipsoid that resembles a cosmic football or a river stone worn flat by a current. This shape, known as an oblate spheroid, makes Haumea utterly unique among worlds of its size. The environment this whirling creates is one of profound gravitational distortion. The centrifugal force at its equator is so strong that if you could stand on its long axis, you would feel significantly lighter than at its poles. The very geology of the world is dictated by this spin. Scientists believe its surface is almost pure water ice, as bright as fresh snow. That icy shell is likely stretched taut over a rocky core, a brittle, crystalline skin holding the form forced upon it by motion. This dizzying rotation likely explains Haumea's other bizarre features. It has 2 small moons, Hioka and Namoka, which may be chunks of ice blasted off the dwarf planet's surface by a colossal impact in the distant past, an impact that might have also given Haumea its incredible spin. Even more astonishing, Haumea possesses a faint ring system, a thin band of debris orbiting its equator. This ring is probably the final, settled dust from that same ancient collision, a halo of wreckage that could not coalesce into a moon or fall back to the surface because the world below is spinning too fast to allow it. So Haumea presents a complete system sculpted by velocity, a tumbling football of ice trailed by moons and girdled by a ring, all because it cannot bear to stand still. This whirling, stretched dwarf planet exists in the frozen quiet of the Kuiper belt, but venture into the crowded heart of a galaxy cluster, and you will find a weather system of staggering violence. Between the glittering galaxies themselves, space is not empty. It is filled with a seething, superheated fog known as the intracluster medium. This is the atmosphere of the cluster itself, a thin but immense ocean of magnetized plasma. The temperatures here are beyond any earthly furnace, reaching tens of millions of degrees, so hot that atoms are stripped bare of their electrons. This creates a soup of atomic nuclei and free electrons, a plasma that glows faintly in X-rays, a sign of its incredible thermal energy. This gas is stirred by immense forces, as hundreds of galaxies, each with billions of stars, orbit the cluster's center of mass. They move through this plasma like ships through a viscous sea, creating turbulent wakes and bow shocks. But the real storms are born from cluster mergers, when 2 of these colossal structures collide in a slow-motion crash lasting billions of years. When this happens, the intracluster gas from each cluster slams together. It cannot simply pass through, so it compresses, heats, and creates continent-sized shock waves that ripple through the intergalactic void for millions of light years. These shock waves are the cosmic equivalent of sonic booms, but generated by the gravitational dance of dark matter halos. They can accelerate particles to near light speed, creating diffuse radio emissions that paint giant, ghostly halos around the merging clusters. This medium also generates relentless cosmic winds. As galaxies speed through this hot plasma, their own interstellar gas can be ram pressure stripped, torn away by the sheer force of the encounter, leaving behind trailing streamers of star-forming material that glow like celestial comet tails. So while the space between galaxies in a cluster appears black and empty to our eyes, it is in reality a dynamic, storm-tossed sea, a place where the weather is measured in shock waves millions of light years long and winds that can strip a galaxy bare. It is a reminder that emptiness is an illusion, and that even the vast gulfs between islands of stars have their own furious climate. That storm-tossed sea between galaxies is shaped by collisions on the grandest scale, but a single, far-off world may be the personal relic of a similar planetary-scale catastrophe. Orbiting a star about 1,700 light-years away, an exoplanet named Kepler-107c presents a profound mystery. It is a world roughly 1.5 times the size of Earth, yet its mass is over 10 times greater. This density is off the charts. For a planet of its volume to be that heavy, its composition must be radically different from our own rocky world. The leading, astonishing explanation is that Kepler-107c is a planetary core, the exposed, metallic heart of what was once a much larger world. The theory suggests a cataclysm of almost unimaginable violence. In the early chaos of its solar system, a protoplanet the size of Kepler-107c may have been struck a glancing blow by another massive object. The impact would not have been a gentle merger. It would have been a cosmic sideswipe of incredible energy, a collision so fierce it did not just crack the planet, but literally sheared away its outer mantle of lighter silicate rock. Imagine two celestial bodies, each larger than Mars, screaming toward each other. In a flash of light and heat that outshines their star, they meet not head-on but at a devastating angle. The shockwave ripples through both worlds, but the target planet gets the worst of it. The outer hundreds of miles of its crust and mantle are not pulverized into debris. They are vaporized and blasted into space, leaving behind only the heaviest, densest part, the iron and nickel core. This metallic heart, now exposed to the vacuum, cools and solidifies into a bizarre new world. The environment in the immediate aftermath would be a hellish, glowing cloud of vaporized rock and metal expanding outward, a temporary, searing nebula illuminated by the fading thermal glow of the impact. Over millennia, the debris would clear, swept away by stellar winds or accreted by other planets, leaving behind a singular, heavy monument. Today, Kepler-107c orbits its sun as a world of almost pure metal. Its surface, if we could see it, would likely be a dark, rugged landscape of iron-rich rock, perhaps dotted with vast metallic plains that cooled from global magma oceans. The gravity on this dense sphere would be crushing, and its magnetic field, generated by that churning metallic core, could be intensely powerful. It is a world forged in a single, shattering instant, a planetary phoenix that rose from its own destruction not as a cloud of dust, but as a gleaming, metallic tombstone for its former self. That exposed metallic world is a monument to a single, shattering collision, but our own solar system is constantly colliding with the galaxy itself. We live within a protective bubble blown by the sun, a vast region of space called the heliosphere. Its outer boundary, the final frontier of our star's influence, is known as the heliopause. This is not a hard shell, but a turbulent, shifting borderland. For over 10 billion miles, the solar wind, a stream of charged particles rushing from the sun at 1,000,000 miles per hour, pushes outward, carving a cavity in the interstellar medium. But that wind cannot blow forever. At the heliopause, its outward pressure finally balances against the inward pressure of the galactic environment, the thin gas and dust that fills the space between stars. This creates a cosmic shoreline, a place where the sun's energetic particles crash and mingle with particles from other stars. The environment here is one of profound transition. The solar wind slams to a halt, forming a termination shock, a region where particles are heated and compressed. Beyond that lies the heliosheath, a turbulent, foamy layer where the solar wind is turned back by the interstellar flow. Finally, at the heliopause itself, the two distinct seas of plasma meet and mix. If you could ride a probe like Voyager 1, which crossed this boundary in 2012, the data would show a sudden, dramatic drop in solar particles and a corresponding jump in galactic cosmic rays. You have left the sun's weather behind and entered the weather of the galaxy, but the journey doesn't end there. As our entire solar system orbits the galactic center, it moves through the local interstellar cloud. This motion might create a structure even farther out, a stellar bow shock. Think of a boat plowing through water. A bow wave forms ahead of it. Similarly, as the heliosphere plows through the galactic medium, it may compress the interstellar material ahead of it into a vast, curved arc, a bow shock spanning light years. This would be the ultimate leading edge of our solar system's journey, a place where the thin stuff of the galaxy is piled up and heated by our passage, a silent, invisible wave we have been riding for billions of years. We are not floating in a static void. We are sailing through a galactic ocean, and these boundaries are the wake and the wave our star creates as it travels. But even a moon orbiting a lonely planet is a simple arrangement compared to what might circle a distant gas giant. For years, astronomers have hunted for icy-moons, moons beyond our solar system, and one candidate stands out as a breathtaking possibility. Around a star over 8,000 light-years away, a planet named Kepler 1625b may host a companion of staggering scale. The data suggests this is not a small, rocky moon like our own. The candidate, designated Kepler 1625b, is potentially the size of Neptune. Imagine that, a moon larger than the planet Mercury, possibly even larger than Earth, orbiting a planet that itself is several times the mass of Jupiter. This creates a gravitational environment of beautiful complexity. The moon would be locked in a delicate dance, feeling the immense pull of its parent planet while also being gently tugged by the distant star. This constant gravitational flexing would generate intense tidal heating within the moon's core, potentially powering a geologically active world. From the hypothetical surface of this colossal moon, the sky would be an alien masterpiece. The primary planet, a banded gas giant, would dominate the heavens, filling a vast portion of the sky. It would rise and set, its phases changing as the moon orbited, casting a soft, reflected light across the landscape during the long planetary night. The sun itself would appear as just a very bright star, distant and small. This moon's own atmosphere, if it has one, could be thick and dynamic, sculpted by the relentless gravitational forces. It is a vista of pure cosmic grandeur, a double-world system that challenges our very definition of a moon and expands our imagination of what kinds of stable, complex environments the universe can engineer. These colossal moons circle worlds of immense gravity, but some stars are locked in an embrace so tight they can no longer hold their own shape. These are ellipsoidal variable stars, binary systems where two suns orbit each other in a frantic, intimate dance. The distance between them is so small that their mutual gravitational pull doesn't just hold them together, it actively distorts them. Each star is stretched, pulled into an egg-like shape by its partner's overwhelming tide. They are no longer perfect spheres, but tidal ovals forever pointing toward one another. As this cosmic egg whirl orbits, our view from Earth changes constantly. When we see the stars side-on, we observe their broad, stretched faces, and they appear brighter. When they turn and present their narrow ends to us, their apparent surface area shrinks and they dim. This regular, rhythmic pulsing in brightness is what astronomers detect as a stellar heartbeat, a gentle but precise flicker in the data. The environment within such a system is one of constant gravitational stress. The tidal bulges are not static. They move and flex as the stars whirl around their common center of mass, generating intense internal friction. This friction heats the stars from the inside out, churning their plasma in ways a solitary star would never experience. This extra heat can alter their evolution, potentially extending their lives or changing their chemical makeup. In the most extreme cases, the stars are so close they may even share atmospheres, their outer layers bleeding into one another in a glowing, chaotic bridge of stellar material. It is a delicate, violent, and beautiful balance, two massive furnaces forever deformed by love, their light beating out a silent rhythm across the light years. Our galaxy is more than a brilliant spiral of stars. It is a prisoner held together by a ghost. This invisible warden is the dark matter halo, a vast spherical shroud that envelops the entire Milky Way. Extending hundreds of thousands of light years into the blackness, this halo stretches far beyond the last visible star, its gravitational influence the true architect of our galactic home. We cannot see it, touch it, or even directly detect the particles that compose it, yet without this phantom scaffold, our galaxy would fly apart. Stars on the outer edges, like our own sun, orbit at speeds that defy the gravity of all the visible matter we can count. The math is clear. There is simply not enough glowing mass stars, gas, dust to keep them from being flung into the void. Something else, something unseen, must be providing the extra gravitational glue. That something is the dark matter halo, an environment defined not by light or heat, but by pure, silent gravity. It is a cosmic skeleton made of particles unknown to our physics, a vast, diffuse cloud through which our entire solar system sails on its 250 million-year journey around the galactic center. We are moving through it right now, feeling nothing as countless billions of these mysterious particles pass through our planet, our homes, and our bodies every second without a whisper of interaction. This halo is the dominant environment of our galaxy, a reminder that what we see is only a decoration, a glittering trim on the edges of a reality built from shadows. The serene, ghostly halo of dark matter is a silent backdrop for far more visible dramas. Against that immense, still canvas, a single star is making a spectacular and violent exit. This is Zeta Ophiuchi, a stellar runaway. It is a blue giant over 20 times more massive than our Sun, and it is not content to orbit peacefully within the galactic disk. Instead, it is fleeing, hurtling through interstellar space at 54,000 miles per hour. But a star of this size does not travel lightly. It blows a fierce stellar wind, a constant torrent of charged particles streaming from its surface. This wind races ahead of the star, a supersonic herald announcing its passage. The problem is the space between stars is not a perfect vacuum. It is filled with a thin, diffuse gas and dust known as the interstellar medium. As Zeta Ophiuchi plows forward, its powerful stellar wind slams directly into this ambient material. The collision is anything but gentle. The interstellar gas cannot get out of the way fast enough, so it piles up. It is compressed, heated, and set aglow, forming a gigantic, curved wall ahead of the speeding star. This is a bow shock, a cosmic wave that looks like the ripple ahead of a speedboat but sculpted on a stellar scale. In infrared images from telescopes like NASA Spitzer, this structure is breathtaking. A brilliant arc of energized gas glowing with ferocious heat wraps around the star's leading edge. Behind it, the star's passage churns the medium into a turbulent, glowing wake. The environment within this bow shock is one of constant, searing violence. Gas is heated to extreme temperatures, dust grains are shattered and vaporized, and magnetic fields are twisted and amplified. It is a temporary, moving frontier of chaos, a bubble of stellar influence that the star carries with it like a personal storm. Zeta Ophiuchi's desperate flight is likely the result of a past cataclysm. Astronomers believe it was once part of a binary pair. Its companion, an even more massive star, lived fast and died young, exploding as a supernova. The sudden release from that gravitational bond catapulted Zeta Ophiuchi away like a stone from a sling, sending it on its solitary, high-speed journey through the galaxy. So this is not just a fast star, It is a survivor, a refugee from a stellar explosion, now writing its story across the sky in light and superheated gas, a brilliant scar marking its path of escape. A triple sunset would be an astronomer's dream, but for a world in the system HD 188753, it could be a daily reality. This is not a single star with planets, but a complex gravitational tango of 3 suns. At the center, a yellow star similar to our own holds sway, with a pair of smaller, orange stars locked in a tight orbit around each other, all whirling together as a single triple-star unit. The gravitational environment here is a delicate and chaotic web, where stable orbits for planets are thought to be nearly impossible. Yet if a world could find a stable path, perhaps far out from all 3 stars, the sky would be a masterpiece of celestial mechanics. Picture standing on its surface as evening approaches your location. The primary yellow sun, the brightest of the 3, begins to dip toward the horizon. But the show is just starting. As it descends, the paired orange stars, appearing as a close-set duo in the sky, follow their own slower arc. You would not witness one sunset but a staggered sequence. First, the main star slips away, bathing the landscape in a deep, golden twilight. Then, one of the orange companions follows, its dimmer, rust-colored light fading. Finally, the last star of the trio sets, completing the triple celestial farewell and plunging the world into true night. The shadows cast during this prolonged dusk would be a tangled, ever-shifting artwork. With 3 distinct light sources moving at different apparent speeds, every rock and ridge would throw multiple, faint shadows that lengthen, merge, and separate in a silent, slow ballet. The light itself would be a blend of spectrums, shifting from sharp white-yellow to a softer, warmer orange hue as each star disappears. Days would be endlessly varied, with the stars rising and setting in different configurations, creating periods of singular, double, or triple daylight. It is a sky of perpetual celestial choreography, a reminder that the simple rhythm of day and night we know is just one possibility in a universe capable of far more complex and beautiful timekeeping. A triple sunset is a spectacle of celestial light, yet the most profound possibilities for life may lie in the absolute and permanent dark. After exploring 50 of the universe's most violent and inhospitable realms, we end our journey with a paradox, an extreme environment defined not by fire, but by a profound, icy quiet that whispers of hope. These are the subsurface ocean worlds, moons like Jupiter's Europa and Ganymede and Saturn's Enceladus. Locked under shells of ice that can be miles thick, they hide global, liquid water oceans larger than all of Earth's seas combined. This is an environment of crushing pressure and eternal night, a sunless abyss where the very concept of a surface is a ceiling of solid ice. No sunlight has ever pierced these deep waters. No wind has ever stirred them. The heat that keeps them from freezing solid does not come from a star but from within. As these moons orbit their massive parent planets, they are flexed and stretched by immense gravitational tides. This constant kneading generates friction in their rocky cores, providing a steady, geothermal warmth that rises through the ocean floor. Imagine diving into such a sea. Your descent would begin by passing through a fractured alien ice sheet, a labyrinth of crevices glowing with a faint blue refracted light from the distant sun above. As you go deeper, that light fades to black. The pressure mounts to hundreds of times that of Earth's deepest ocean trenches. You are now in a realm of total darkness, suspended in a world-spanning ocean, with only the gentle, convective currents from hydrothermal vents on the seafloor to guide you. Around those vents, in the absolute dark and crushing pressure, chemistry becomes the engine for possibility. On Earth, we find entire ecosystems thriving around deep-sea hydrothermal vents, life that draws its energy not from the sun, but from the minerals and heat bubbling from the planet's interior. This is the profound promise of Europa, Enceladus, and Ganymede. They represent the ultimate extreme, not of destruction, but of secluded, sheltered potential. In the freezing, lightless oceans of these distant moons, against every harsh condition we once thought necessary, the basic ingredients for life, liquid water, chemistry, and a stable source of energy may have found a way to combine. After crossing deserts of molten glass and storms of diamonds, after witnessing stars torn apart and galaxies fleeing into the void, we find that the universe's most astonishing extreme might be its quiet, hidden capacity to cradle life in the most unexpected places. The final fact is not about an end, but about a beginning waiting in the dark. From the hidden, life-cradling oceans of icy moons to the screaming stellar winds of runaway stars, our journey across 50 cosmic extremes reveals a universe of breathtaking violence and impossible beauty. We have sailed on seas of molten rock, witnessed the slow-motion disintegration of worlds within the Roche limit, and felt the silent, chilling pull of dark matter. We have seen stars flung from their galaxies, planets stripped to their metallic cores, and black holes that warp the fabric of space into natural telescopes. Each of these environments, from the crushing pressure of a neutron star's surface to the eternal twilight of a tidally locked world, exists as a natural laboratory where the laws of physics are stretched to their absolute limit. They are not mere curiosities, but fundamental expressions of what reality can do when freed from the gentle constraints of our own temperate corner of space. This voyage challenges more than our sense of scale. It confronts our very imagination. The universe operates on a canvas so vast and with a palette so strange that the line between science fiction and scientific fact continually blurs. These extremes are not flaws or errors in the cosmic design. They are the design. They show us that water can become a seething supercritical fluid, that gentle starlight can sculpt colossal nebulae, and that the emptiness between galaxies holds storms of its own. They prove that the conditions we consider necessary for life are just one narrow band in an infinite spectrum of possibility. By studying these alien realms, we are not just cataloging distant wonders, we are stress-testing our understanding of physics, chemistry, and geology itself, learning the true rules of the cosmos by seeing them broken and remade in the most spectacular ways. Now the question turns to you. After this mind-bending tour from the heart of stars to the voids between galaxies, which extreme environment left the deepest mark on your imagination? Was it the relentless supersonic glass rain of WASP 76b, or the patient frozen icebergs sailing on Pluto's nitrogen seas? Perhaps it was the haunting solitude of a hypervelocity star, or the violent creative chaos of the Tarantula Nebula. Share your thoughts in the comments below and let us know which cosmic wonder you would want to explore next. If you enjoyed this journey to the edge of reality, be sure to subscribe and join us as we continue to unravel the universe's greatest mysteries, one astonishing discovery at